We're going to look at a type of implicit differentiation problem called related rates. So in this section, all variables are functions of time. If we've got something in the XY plane, it's moving. So its location is given by the coordinate, but also it's moving from that point. So there's a rate of change in each of those coordinates. So position is given by essentially an ordered triple if we're in 2 dimensions, time, x, and y, where x is a function of time and y is a function of time. And if we're doing word problems, then all our variables are functions of time. And we're looking at the rate of change in x with respect to time. With respect to time is given by dx dt. Similarly, dy dt is the change in y with respect to time. Except our equations aren't going to have the variable t present. It will be the implicit variable. That time is the independent variable and everything else is a function of time. So when we take the derivative of something, for instance, suppose we're taking the derivative with respect to t of either an x or a y to a power. Then we get the ordinary derivative. And then we get an x prime term that we're going to call dx dt. And the derivative with respect to t of y to a power is done the exact same way. In this section, we're going to have an equation that relates our variables at any time. Then we're going to look for an equation that relates their rates of change. And we generate this equation by taking derivatives. For example, suppose x is a function of time and y is a function of time, where x squared plus 3xy plus y squared is 9. Find an equation that relates the rates of change in x and y. And so this time we start with our equation and we take the derivative of each term with respect to time. We still have things like derivatives of sums, derivatives of products, functions, and so on. So we start out this way. This is what we're thinking. We take the derivative with respect to time of the entire equation. We'll do that to both sides of the equation. So here we are taking the derivative of x squared. And like I said over here, you get the 2x to the first power, but then you multiply it by the dx dt. In here, we'll use the product rule, where 3x is the first term and y is the second term. And we'll do the first times the derivative of the second. And the way I'll write the derivative of y is dy dt plus the second times the derivative of the first. Derivative of 3x will be 3dx dt. Now we're out here on the end, taking the derivative of y squared. We get 2y dy dt, ordinary derivative times the associated y prime term. And then on the right-hand side, the derivative of the constant. Then in our application problems at this step, we'll be given some information about 3 of our 4 unknowns. We have x, y, dx dt, and dy dt. And we'll have to solve for the missing one. Okay? All right, so I sent you some problems. Did anybody make copies of them? I've got some if you want some. Gotta make my finger, I can't put papers apart. So around to the other side, so around. You guys take care of your on yours. Oh, no. Oh, no. Sorry.
I need one.
Too bad.
Okay,
Quit that.
You gave me enough.
Where did this thoughtfulness come from? I didn't want to have to write all these on the board. I don't know if I left you enough room to work them, but write real small. Okay, so here's a for instance. It's a stupid example, but there's a bead moving around on this graph. All right, so I don't know what the graph looks like, but there's a bead moving around on it. At some time, you know, the x coordinate is changing at a half unit per second. How fast must the y coordinate change so that the bead stays on this little graph? So essentially the graph is some sort of minus y cubed graph. So maybe it looks something like, I really don't know. Maybe it looks something like this. That's the graph of 3y cubed plus 4x is equal to 28. And at some instant, the bead is at the point 2,1. And we're told that the x coordinate is increasing at a rate of half a unit per second. So the rate of change in x with respect to time is a half. So in order for this bead to stay on the graph, we need to find the rate of change in y with respect to time. And I don't know if the graph looks like that, but that's just a for instance. So we take the equation that relates the position of the bead at any time t. We're going to do this. We're going to take the derivative of each term and get our related rates equation. And then I've given you an x, a y, and a dx dt, and we'll solve for the missing dy dt term. This one's a little bit easier to take the derivative of. There's only 3 terms. No product rule anywhere. So you start with the position equation, take the derivative of both sides with respect to t, and generate the related rates equation. The derivative of 3y cubed, as that says over there, is the ordinary derivative, 9y squared. And now the chain rule part, we multiply by dy dt. So what do you think the derivative of 4x is? Good. and then the derivative of 28 is 0. This is called the related rates equation. We're looking to solve for dy dt. How fast is the y coordinate changing? So we put the numbers in everywhere else. The y value is going to be 1. We don't have any x's. If there were, we put the 2 in for x. And the dx dt is a half. And so we have 9 times 1 squared. dy dt is what we're going to solve for. Plus 4 times dx dt is equal to 0. So we have 9 dy dt. 4 times a half is 2. I'm going to push it to the other side, make it a negative 2. And so dy dt is minus 2 over 9. So the negative sign means that the y coordinate is decreasing at a rate of 2/9 units per whatever time period I gave you, or seconds. So we have to look for words like how fast. When you see that in your problem, that's a change with respect to time. How fast is something changing? So let's make something a little bit more reasonable than a bead swinging around a graph. And most of these from here on out, we're going to come up with our own equation based upon the description of the problem. Let's read the second one here. Petroleum from a leaking offshore well forms a circular oil slick on the surface of the water. The radius of the slick is increasing by 0.3 of a kilometer per day at the instant when the radius is a half a kilometer. Find the rate at which the area of the oil slick is changing. So visualize a circle growing in size, staying circular shape. We've got some mention about the radius. And we're told that the radius is increasing at a rate, so that's a dr dt, of 0.3 of a kilometer per day. dr dt 0.3 kilometers per day. But that it depends on how big the instant is. So we get another measurement here at the instant when the radius is half a kilometer. So that's a fixed measurement. So that's just r, not its derivative. And then we're asked to find at what rate is the area changing. We need to find dA dt. So we're talking about the area of a circle. Who knows the formula for the area of a circle? So that's the equation that we start with. That's the equation at any time t. That's the equation we're going to take the derivative of. Okay, so I'm not going to write this step down. We're just going to think this step. We take the derivative of each of those terms. On the left side, we take the derivative of a with respect to t, and that's what we get, dA dt. Pi is a constant. We can factor it out. And now we're going to take the derivative of r squared. And what will we get? And there's our related rates equation. We're looking for the entity on the left-hand side. We've got a number to put in for R and dr dt. So we fill everything in and then interpret our answer. So I have dA dt is pi times 2 times a half times 0.3. The 2 times a half is just 1, so I get 0.3 times pi. That's a change in area. Area is going to be measured in square kilometers. So I'm going to interpret that as saying that the area is increasing, since it's positive, by 0.3 pi square kilometers per day at that instant. Right, it probably grows real fast at the beginning and slows down as the radius grows. Yes.
So like whenever we found the derivative of the area, why doesn't pi go to 0?
I didn't do the product rule. I did the constant times a function rule, where you pull the constant out, take the derivative of the function, and then put the constant back on. If I were going to do the product rule, then in its turn, I would have a 0 as that derivative.
So you just think of pi as a constant.
Yes.
I have a question. So why did you put the GDR?
Because R is changing with time. So this part here is the chain rule. You take the derivative of the outside rule, which is the R, but then you have to go inside and take the derivative of the time function. So they're all going to be applied functions of time. You're always going to slap on a whatever the variable name is, dt, after you've taken the derivative of that variable. Okay. All right, number 3. Gas is being pumped into a spherical balloon at a rate of 5 cubic feet per minute. What kind of thing is measured in cubic feet? So that's a change in volume with respect to time. If the pressure is constant, find the rate at which the radius is changing when the diameter is 18 inches. So our balloon is a sphere. The change in volume with respect to time is that 5 cubic feet per minute. Find the rate in which the radius is changing when the diameter is 18 inches. So we have a kind of a preliminary step here. The diameter is twice the radius. I don't care about the diameter in this problem. So if the diameter is 18 inches, the radius is 9 inches. Then I need to convert inches to feet. So in other words, radius is 9 inches. How do I convert that to feet? Divide by 12. So that's 9 over 12, or 3/4 of a foot. Now here's the fun part. I get to see if you guys know the volume of a sphere formula. 3/4? 4/3 pi r cubed. Very good. That's the formula we start out with. That's going to be our position formula. Then we generate the related rates formula by taking the derivative with respect to t. So give it a shot. Treat the 4/3 pi as a constant when you're taking the derivative on the right-hand side. So while I erase, let me see if you can take the derivative of that with respect to t. Is that on backwards? No, that's tickling my nose. No better. Anything else on backwards? All right, so tell me what your derivative looks like.
dv over dt
Yep.
is equal to 4/3 pi and then 2r squared.
How about 3r squared? Times
dr dt.
dr dt. Bring power down, raise it to 1 power less. Dr dt is in effect multiplied by the derivative, the inside function part. The 3's will cancel. So I have 4 pi r squared dr dt. And now we're going to put our numbers in. Let me go ahead and cancel the 3's. We are going to solve for dr dt. So we should have numbers that go everywhere else. dv dt is 5, and r is going to be that 3/4. So 5 is equal to 4 pi times 3/4 squared times dr dt. Three-fourths squared is 9/16. 9/16 times 4 gives me 9/4. So this becomes 9 pi over 4 dr dt is equal to 5. I'm going to multiply by 4 and then divide by 9 pi. So I get that dr dt is 20 over 9 pi. And so we'll put the units on that. It's positive, so we're going to say that the radius is increasing at a rate of 20 over 9 pi feet per minute at that instant. So again, in a situation, 2 or more things are changing over time. A change in one causes a change in the others, and then we're going to use calculus to find the measures of those. Any questions? All right, number 4. Is there a number 4?
Yeah.
A 20-foot ladder leans against the building. If the bottom of the ladder slides away from the building at a rate of 2 feet per second, how fast is the ladder sliding down the building when the top of the ladder is 12 feet above the ground? Let me try to make a diagram here. Here's the building. Here's my awesome artwork. That's a ladder, right? You just kind of feel that ladder. There's the ground. The ladder's not even touching the ground. The bottom of the ladder is sliding away from the building at a rate of 2 feet per second. The ladder stays at 20 feet throughout the whole problem. How fast is the ladder sliding down the building? At the instant when the top of the ladder is 12 feet above the ground. So we've got action behaving like a triangle where the 2 legs change in size. Got any equations to relate the legs of a triangle to a hypotenuse? Okay, so I need a couple of variables for the things that are changing. I'll use X and Y. I'm gonna say that this is horizontal distance is X and the vertical distance is Y. And so by the Pythagorean theorem in this picture, I have that X squared plus Y squared is 20 squared. Then we are looking to find dy dt. If dx dt is 2, and the instant in consideration is when y is 12. So now that's our problem. Find dy dt if dx dt is 2 when y is 12. So I put everything given in the language of the problem. I wrote down my equation for the position at any time t. And now while I erase, you guys generate the related rates equations. It's a quickie, right? Call out the related rates equation. Okay, now let's put everything in. We're looking to find dy dt. So this we don't need anything for. Let's put our numbers into the other spots. 2x. I don't have an x just yet. Let's hang on to that. Let's just leave a gap for that. We'll come fill it in. dx dt is 2. Y we said was 12. dy dt is what we're solving for. I left those parentheses for x. That's x at the instant when y is 12. So we freeze frame the action when y is 12 to figure out what x is. That's 12. That's 20. Figure out x at that instant. What'd you get? Probably working harder than you need to. 12 is 3 times 4. 20 is 5 times 4. What should the leg be?
That's equal 16.
16. It should be 4 times 4, right? It's a 3, 4, 5 triangle. Right? 3, 4, 5 triangle. So x is going to be 16. So we put the 16 in the parentheses over here. And then we're going to solve for dy dt. So let's see, 4 times 16 is 64. 2 times 12 is 24. Subtract 64 from both sides. And then I'll divide by the 24. Let's see, 8 goes into both of those. That's a negative 8/3. So we can interpret the negative sign being that the top of the ladder is coming down the wall. at a rate of -8/3. I guess we don't need the minus if we say it's coming down. 8/3 feet per second. So here you are standing under this ladder. Just for the sake of argument, let's assume that you're, I don't know, 5 feet tall. At that instant, that ladder is coming down the wall at -8/3 feet per second. How many seconds before it conks you on the head? Well, 1 second later, instead of being 12 feet high, that's what, 2 2/3? So instead of being 12 feet high, it's 9 1/3 foot high. So it still hadn't hit you. 1 second later, 9 1/3 minus 2 2/3. It's 6 2/3 feet high. Uh-oh, that's 2 seconds. 1 more second later, it has hit you. It's 4 feet high, it's hit you. You're out cold. Just a little bit more than 2 seconds later. So next time you're standing under a ladder and this is happening, you've got about 2 seconds to do your calculations and realize you need to get out of there. All right, flip them over. Okay, there's a street light. A boy 5 feet tall walks away from the street light at a rate of 4 feet per second. If the light is 6 feet above ground level, how fast is the boy's shadow lengthening? So let's get a picture of this boy walking away from a 16-foot tall street light. All right, there's the street light. There's the ground. The boy walking away from it. He's going that way at a rate of 4 feet per second. In the meantime, the light is shining down and generating a shadow. So here's his shadow. We want to know how fast his shadow is lengthening. So we know that the boy is 5 feet tall. So we need to put variables for the things that are changing over time. The distance between the boy and the wall is changing over time, and the length of his shadow is changing over time. This light pole stays at 16 feet tall. But if the boy is right here, this distance is changing over time. And if the shadow is right here, that's changing over time. So I'm going to call the distance between the boy and the wall X and the length of the shadow S. Those are what's changing over time. This stays at 5 feet. And now I need some equation that relates those entities to each other. This is changing over time, but they're not giving any information about it. So I don't want to put a variable there because I don't know anything about it. So does this picture make you think of anything? similar triangles. We've got the big triangle whose leg is 16 and other leg here is x plus s. And then we have a little triangle whose leg is 5 and whose other leg is s. So we can set up proportions by similar triangles. Since we're going to take derivatives, let's put the variables on top of the proportions. We can say big leg is to the height as little leg is to the height. X, that's not 5, that's an S. We chose an S and a 5 in the same problem. By similar triangles, X plus S is to 16 as S is to 5. And we want to find what? How fast is the shadow lengthening? So in my variable, the shadow is S. We need to find ds dt when we know that dx dt is 4. Okay? And then maybe to help you take derivatives, I can say that that 1 over 16 and that 1 over 5 are just constants. And we have 1 over 16 times x plus s is equal to 1 over 5 times s. And then we can do to the 1 over 16 and the 1 over 5 like we did to the 4 pi. Just hang on to it, take the derivative inside, put the constant back on. Okay, so that's our equation that relates the lengths at any time t. Let's take the derivative of each term. Again, the constants can come out. Then you can go inside the parentheses and take the derivatives of those. You'll get dx dt plus ds dt. And on the right-hand side, you get 1/5 times ds dt. So what that's telling me is the position of the boy from the light pole has no bearing, just how fast he's walking. It changes the size of the shadow. He's walking at a rate of 4 feet per second. So this number is 4, and we've got to solve for ds dt. So how about we distribute the 1 over 16? 1 over 16 times 4 is 4 over 16, which is 1/4. Then I get 1 over 16 ds dt is equal to 1 over 5 ds dt. I'm going to move this to the other side by subtracting it. So let's get a common denominator between the 5 and the 16. 5 times 16 is 80. So let's write that as something over 80. That's 16 over 80 minus 5 over 80. So these two combine to give me 11 over 80 times ds dt. Now 1/4 is equal to 11 over 80 times ds dt. We'll divide by 11 over 80, which is the same thing as multiplying by 80 over 11. That's 20 over 11. positive number. It tells me how fast the shadow is growing. The shadow is growing at a rate of 20/11 feet per second. Okay. So we used an area of a circle, we did a volume of a sphere, we did Pythagorean's theorem, and now we did similar triangles. And well, we did something else. Oh, just the bead moving on a graph. Okay, let's look at number 6. A balloon is rising vertically from a point that's 200 meters from the observer. The angle of elevation between the observer and the balloon is increasing by pi/200 radians per second when the angle of elevation is pi/4. How fast is the balloon rising at this time? So let's get the balloon going up in the air. There's the balloon. It's rising. Somewhere there's an observer. He stays 200 feet away from the balloon where it was left off. Going straight up. That's not in Lubbock. It's not blown away. This is going straight up. The angle of elevation between the observer and the balloon. So here's the observer's line of sight. There's the angle of elevation. Let me put a theta there since that's changing. Is increasing at a rate of pi/200 radians per second. So that's a measurement per second. That's a d theta dt. And then we've got an instantaneous measurement for theta. That occurs when theta is pi/4. How fast is the balloon rising at this time? Be whatever dt. So I need a variable over there. All right, let's just call that a y since it's going up. dy dt is what? And some measurement here. Okay, I think that's all the pieces of information we have. We have an angle changing and a height changing. 200 stays put. When you look at that picture in this right triangle, you've got an angle, you've got an opposite side, and an adjacent side in a right triangle. That make you think of anything? Which one's opposite over adjacent? Tangent. Tangent of that angle is the opposite side over the adjacent side. That's going to be our starting equation. So we take that equation, take the derivative with respect to t. What's the derivative of tangent of theta? Secant squared theta. Secant squared theta times d theta dt. On the right-hand side, think of the 1/200 as a constant. And now go and take the derivative of the y. And you get dy dt. I have a d theta dt, I have a theta, and we're looking for dy dt, so we have numbers for everything. Let's put the numbers in. So you start with a position equation, take its derivative, then put in the numbers at the very, very end. So we need to figure out secant squared of pi/4. d theta dt is pi/200. Secant is 1 over cosine. What's the cosine of pi over 4? Root 2 over 2. And then we're going to square it because the secant is squared. At one stage in the game, I'm going to multiply by 200 to solve for dy dt. I'll do it now. So those 200s cancel. Square root of 2 over 2 squared gives me 2 over 4, which is a half. I have a half down here, flip it, and it gives me 2. 200s cancel, so I have 2 pi is dy dt. So the balloon is rising. At a rate of 2 pi feet per second, about 6 feet a second. Okay. All right, we'll work the last 2 next time, but I think you've got enough to get you going on your web work. Work some more on Wednesday, and then Wednesday we'll start section 8 of chapter 3. That'll be the last section of chapter 3 on Wednesday.
Where did pi over 4 come from for theta?
I gave that to you. It was given in the problem. Okay, the angle changes at some particular instant. All good? All right.